After defining the displacement gradient, we are in a better position to define our strain in terms of the displacement gradient. The strain tensor can be written as half the displacement gradient H plus the displacement gradient transpose. Component wise, it can be written as strain Ij is equal to half Hij plus Hji, where I shows the row and J shows the column. So let us put values and see whether this makes sense. Hij would be equal to Uij. So Ui comma j is curly Ui by curly xj. Uji on the other hand would be curly U by curly xi. This is equal to strain Ji. Even if we change the position of these two, we will get the same result. We already discussed our Uij and Uji when we were working out our equations for the strains. Please note that by exchanging the position of Uij and Ji doesn't change the strain. So that tells us that the strain Ij is equal to strain Ji. In order to find out strain 1, 1, we can have I and j equal to 1. So that makes u 1 1 twice and 2 get cancelled with the 2 in the denominator and we get u1 1, which makes sense. Similarly, strain 1 2 is equal to half u1 2 plus u2 1. u1 2 plus u2 1 has been called as gamma 1 2 above. So according to this definition, our strain 1 2 is equal to half gamma 1 2. In matrix notation, the strain tensor can be written as follows. Please note that in the strain matrix, the diagonal terms are giving us what's called the volumetric strain. So strain 1 1, strain 2 2, and strain 3 3. These are the strain in the axial direction. So our strains in the axial directions, that's given by the diagonal components. That's why we can write this as summation of I strain II. So adding all of them, we get what's called the volumetric strain. So that is change in volume divided by original volume. Now let us briefly discuss that the strain does not reflect any rigid body motion. A rigid body motion is characterized by the fact that the length of any line element within the body remains unchanged. So imagine we have a body which is a cube shaped and there we mark 2 points which are shown by the red blobs and join the blobs by a line. Now, in order to describe the translation in the rigid body motion, we can say that we define our two formations as y1 is equal to x1 plus a and y2 is equal to x2 plus b. Imagine this body is in x1, x2 space. We define two displacements y1 and y2 as x1 plus a and x2 plus b. So based on our earlier definition of deformation of deformable body, we said that in the deformed configuration, y is equal to x plus u. Thus, in the deformed configuration, we have y is equal to x plus a. So that gives us a displacement u1 value equal to a and displacement u2 value equal to b. Plugging the values in the displacement gradient tensor, we get all the components as 0. Please note that we have considered only the first 4 components of the displacement gradient because we are dealing with a 2D space. So getting h is equal to 0 means that strain is also equal to 0 based on this definition of strain. Now let us check what will happen if we have a very small rotation. So we define our displacements now as u1 equal to minus beta x2 and u2 is equal to beta x1. Please note that u1 is the displacement in x1 direction. So that displacement is negative, and u2 is the displacement in x2 direction, which is positive. We are just simply using the sector length formula. S is equal to r theta. Now again, plugging values in our displacement gradient matrix, we get u11 equal to 0, u12 equal to minus beta, u21 equal to beta, and u22 equal to 0. Now, we have the displacement gradient, which is not 0. If we put the value in our strain matrix, we get everything 0. So these two examples clearly demonstrate that if we have a rigid body translation or rigid body rotation. In other words, if we take any 2 points within the body and move the whole body by some distance or rotate the whole body by a small rotation, there won't be any strain induced in the system or in the structure, because the rigid body motion is characterized by the fact that the length of any line element joining any 2 points remain unchanged. The only way strain can be induced if these 2 points they either move apart or they move closer to one another. So in these both examples, the red line stays the same after the displacements. This clearly shows that the displacement gradient has got rigid body displacements incorporated, whereas in the strain matrix we don't have any rigid body displacements. Now we move to transformation of strain components. A transformation of strain component is one of the fundamental concepts in structure mechanics involving the change of strain components from one coordinate system to another. As we discussed, the strain components describe how an object deforms under the applied forces or loads. First of all, we will discuss the transformation of strain in a 2D space, and then afterwards we will discuss the transformation in the 3D space. The transformation of strain components between the coordinate system will be governed by a linear transformation that is similar to transformation of vectors. So we can see that there is an element having the stress components shown. The element is subjected to general state of plane stress. The reason we are calling it plane stress because we are ignoring the stresses in the third dimension. The normal stresses are assumed to be tensile and they elongate the element in x1 and x2 direction, whereas the shearing stresses distort the element through the shear strain gamma 1 2 as shown in this figure. Our coordinate axis, which is shown in purple, corresponds to the left corner of the element. Or in other words, the coordinate axis has got an origin at the left corner of the element. The effect of these strains on any line element OA is shown in this figure. So we have the element which is OA, and that OA changes its angular position by a very small amount that we call beta, and also OA is elongated to OA dash. The movement of A to A dash is the vector sum of the axial elongations and the shear distortions. So horizontally, we say that A has moved by strain 1 into D1, where D1 is the horizontal dimension of this element. So this element is considered horizontally as D1 and vertically as D2. The reason strain 1 is multiplied with D1 is that we are trying to find out our deformation, which is equal to strain by the original length D1. Using the same logic, we can multiply the strain 2, which is in the x2 direction, to the original length D2. And the shear distortion gamma 1, 2 can be multiplied with D2 in the x1 direction. So, as we can see in this figure, the movement towards the left is gamma 1, 2 times D2. In other words, this is just tangent theta is equal to perpendicular by base. Since we are dealing with very small distortion, so tangent theta is approximately taken equal to theta. And theta is gamma 1, 2. That gamma 1, 2 is multiplied with the base D2 to get the shear distortion, which is gamma 1, 2 D2. Please note that this movement of A is highly exaggerated to show how the vector sum may be resolved into two components, that is, one parallel and another one perpendicular to OA. The parallel component A dash represent the increase in length of OA, whereas the perpendicular component A double dash causes the change beta in the angular position of OA. The magnitude of A dash is found by projecting strain 1 D1, strain 2 D2 and gamma 1 2 D2 upon the direction OA. Thus, we get A dash is equal to strain 1 D1 cos theta. So strain 1 D1 component along OA plus strain 2 D2 sine theta, which is this one, strain 2 D2, and its component along OA minus gamma 1 2 D2 cos theta. So gamma 1 2 D2 and its component along OA. Please note that instead of finding the components upon OA, we can also find it upon OA dash because the angle between OA and OA dash is very small. Please also note that along OA dash, strain 1 D1 is in the direction OA dash. Strain 2 D2 is again in the direction OA dash, whereas gamma 1 2 D2 is in the direction A dash O. That's why negative appears in the case of gamma 1 2 D2 cos theta. If we assume that OA is equal to ds, or in other words, the length of OA is equal to ds, divide A dash by ds, we will get the extension of OA, which is equal to strain 1 D1 cos theta by ds, strain 2 D2 sine theta by ds minus gamma 1 2 D2 cos theta by ds. Since d1 by ds is cos theta, d2 by ds is sine theta, and d2 by ds again is sine theta. Plugging the values, we get the extension of strain A in terms of strain 1, strain 2, and gamma 1, 2. The angular deviation beta can be found in a similar way. We have to divide A double dash by the length ds in order to determine our angular deviation. Projecting the movement of point A on the direction perpendicular to OA, we obtain AA double dash as strain 1 D1 sine theta minus strain 2 D2 cos theta minus gamma 1 2 D2 sine theta. Once this is found, again we can divide this whole expression by ds and plug the values of d1 by ds, d2 by ds. We get beta equal to strain 1 cos theta sine theta minus strain 2 sine theta cos theta minus gamma 1 2 sine square theta. As we know that the total change in the right angle between OA and its normal OB defines the shear strain for an element that is located theta from the x1, x2 axes. That is why we have to work out our angular deviation OB, which is at theta plus 90 degree. So plugging theta plus 90 degree in the beta equation, we get beta dash as minus sigma 1 sine theta cos theta minus strain 1 sine theta cos theta plus strain 2 sine theta cos theta minus gamma 1 2 cos square theta. Please note that beta and beta dash rotate in the opposite directions. So their absolute sum is equal to their algebraic difference. That's why the absolute sum is taken as beta minus beta dash. So, and that gives us strain 1 2 sine theta cos theta minus strain 2 2 sine theta cos theta plus gamma 1 2 cos square theta minus sine square theta. Thus, we have derived the axial strain and the shear strain for the 2D element. Now we will apply the same concept in 3D. In 3D, the strain is typically represented using a strain tensor. This strain takes the form of 3 by 3 matrix. The transformation of strain component between the coordinate system is governed by a linear transformation, and we will now discuss how the transformation strain component work. We assume a body that is made up of infinite fibers. We take one fiber which is in green color when the body is in the unloaded state. After loading, the green fiber turns into red fiber due to extension and shear deviation. We can say that every fiber within the body deforms that would involve stretching, squishing, and shearing. If we assume that this body is made up of infinitesimal small spheres, every sphere has got bunch of tangent vectors dz pointing in every direction, as shown over here. After deformation, as we said, the green fiber is stretched and sheared into the red fiber. So we can say, based on our sphere analogy, that after deformation, the sphere is changed into ellipsoid of infinite bunch of tangent vectors dx. So in 2D, we can see a circle which has got infinite tangents of dz magnitude in all the directions. After the application of the load, this circle is stretched into an ellipse, and all these dz vectors are stretched into dx. Please note that some of the vectors are stretched where other vectors are squished. Similarly, in the case of shear, we take two concurrent dz vectors and calculate the angle between them after the application of the load. If the angle has changed, that means shear deformation has taken place. An interesting point to see is that even in the case of simple stretch, we have some of the concurrent vectors whose angle changes or shear deformation take place. Later we will see that there are some direction in which the extension is maximum. Those will be called as the principal directions. Please observe that every two concurrent vectors, they undergo shear deformation as we stretch our element, except the orthogonal ones. The orthogonal one angle is 90 degree before the stretch, and after stretch also they have the angle 90 degree. The orthogonal ones are shown by the big green arrows. Now consider that we want to find out the strain vector on an arbitrary oblique plane P. So we take the tangent plane and try to cut our sphere to an arbitrary oblique plane. For clarity, we can now show this system in the form of prism. In this prism, we have got the outward drawn normal of the plane ABC, whose deformation we are interested in. The unit normal vector to plane P is equal to Lx1 vector plus mx2 vector plus nx3 vector, where L, M, and N are the direction cosines, and x1, x2, x3 are the unit vectors corresponding to our 3D vector space. In this prism, we have the plane P and we have three faces, that is OBC, OBA, and OAC. Every face on this prism will have the corresponding DZs and DX vectors. Thus, we can say that we are imagining a point which has got infinite fibers coming out, and these fibers have got tangents. Those tangents will appear on all the four faces of this prism. We can find out the resultant of all those displacement tangent, and that displacement tangent can be converted into strain by dividing them by the original length in the corresponding direction. Now take an example of the face OBN. This face has got outward drawn normal in the x1 direction. We find out the resultant strain, strain 1, corresponding to this face as equal to the sum of three strains, one axial plus two shear. So the strain vector of the face having outward drawn normal in x1 direction is equal to the axial strain time x1 unit vector plus the shear in x2 plus the shear corresponding to the force in the x3 direction. Please note that in the case of this prism, the resultant strain of fibers of particular face is due to the deformation of all the fibers on that face. More specifically, if strain 1 is the resultant strain of all fibers on face having its outward drawn normal in the x1 direction corresponding to the face OBA. Similarly, strain 2 is the resultant of all the strains in fibers on face OBC whose outward drawn normal is in the direction x2. The same argument is applied for the face OAC. The strain 1 vector can be decomposed into three vectors. One is the vector which is in axial direction in the direction x1, and two are the shear components of the strains. These are shown over here. So strain 1 is decomposed into the axial strain in corresponding to x1, then the shear strain corresponding to x2, and shear strain corresponding to x3 direction. Similarly, the strain corresponding to the face OBC can be decomposed into the axial strain and the two shear strain. Same argument will apply for strain 3. As we said that the outward drawn normal for the reference plane BNC is Lx1 plus mx2 plus nx3, thus strain P, which is the resultant strain of all the fibers that have got tangents on the plane BAC. That is equal to L times strain 1 plus M times strain 2 plus N times strain 3. Please note, L, M and N are the direction cosines. Additional explanation about the direction cosines can be found in mathematical preliminaries. L is the direction cosine corresponding to x1, M is the direction cosine corresponding to x2, and N is the direction cosine corresponding to x3. So, in other words, we have tried to bring the strains in line with the direction cosines of the particular phase. Or, in other words, we have brought the strains in line with the outward drawn normal of a particular face. Please note, looking at the prism, the strain 1, 2, and 3, which are on the faces OBA, OBC, and OAC respectively, they are oriented in a random direction. If we multiply these strains with the respective direction cosines, we will bring the strain in line with the outward drawn normal of the face. For example, strain 1 is the strain corresponding to face OBA, and this strain vector is for any fiber whose tangent vector is in a random direction. If we multiply strain 1 with the direction cosine L, that would bring our strain 1 vector in line with the outward drawn normal of the face OBA. The same argument can be applied for the face OBC and OAC. Therefore, the strain P can be equated to the strain corresponding to the face OBC, OBA, and OAC in the form shown over here. Strain P can also be decomposed into three components as strain P1, strain P2, and strain P3 in x1, x2, and x3 direction. As we have discussed that each strain is made up of one axial and two strains, we can compare the coefficients of x1 and x2, x1, x2, x3 and get the components strain P1, strain P2, and strain P3 in terms of strain 1, strain 2, and strain 3. Once we find out the component strain P, we can take a dot product with N and find out the strain corresponding to the outward drawn normal of the face ABC. The dot product equation is given as L square strain 1 plus M square strain 2 plus N square strain 3 plus 2MN strain 2 plus 2LN strain 1 plus 2LM strain 1 Having worked out strain P and strain Pn, we can use Pythagorean theorem to get our shear strain on the face ABC.